Okay, guys, here's another example problem, and hopefully again I don't have to do or explain how to analyze a voltage source and a current source, or so you should be able to do a lot of these example problems by yourself. However, we're going to continue doing some example problems in the regular lecture, so consider these to be supplementary. So very quickly, here is one of the examples, and you have a voltage source connected. At time t equals to 0, the switch opens. So when the switch gets open, the excitation source gets removed, right? The amount of the energy that is stored in the inductor will start to be released and gets dissipated in a 15 kilo ohms and a 15 kilo ohms resistor, both of them. So at time t equals to 0, the switch is going to open, and where we have to deal with the natural response of a circuit. So let's find all of these things, okay? Solution. So the very first thing it is asking us to do is to find the value of the current I1 and I2 just before the switch opens, right? Both of these currents. I have to find both currents before switch opens, right? 0, negative. So this means that I have to solve circuit for t is less than 0. T less than 0 means that your switch was closed. So let's make a circuit for a switch closed where we have this resistor, this resistor, this resistor, and I'm going to draw a circuit in a second, inductor in a second. So this is 9 volts, 15K, 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 right? I2, I1, right? And the switch was closed. Again, when the switch was closed at t is less than 0, and you have an excitation source, so this excitation source must be providing energy in the magnetic field of an inductor, right? And after some sort of a steady state or some time, this inductor must have been a short circuit. So I am going to convert this into a short circuit here at t equals to less than 0. Okay, so let's find the values of the currents. I am interested in finding the value of I1 and I2. Okay, so let's see how much of the current IS that is flowing over here. So let's first find the value of the IS. In order to find the value of the IFs, I know that both of these resistors, 15K here and 15K here, are in parallel. So I can, so for example, if 15K in parallel with 15K, they are exactly the same, 15 times 15 over, right? So 15 times 15 over 30 is gonna come out to be 7.5 kilo ohms. So we can kind of simplify this circuit by redrawing this circuit as this: 9 volts, 15K, 7.5K, and here is the IS that is flowing. So IS can easily be found by doing 9 volts divided by 15K plus 7.5K. So it is going to come out to be 0.4 milliamperes, right? So this IS at 0, negative, is 0.4 milliamperes. However, right, so if this IS is flowing over here 0.4 milliamperes and you come across two resistors that are equal, right, you can apply a current divider rule, or the current is going to divide equally, right? So this means that I1 0 negative equals to I2 0 negative, right? So that should be equals to your original current, 0.4 milliamperes divided by the resistor, 15K divided by the sum of the resistors, 15K plus 15K, current divider rule, and this is going to come out to be 0.2 milliamps, right? So your I1 0 negative equals to I2 0 negative equals to 0.2 milliamps. Okay, so we are done with the first one. Let's find the second part. In the second part, we have to find both of these currents right after the switching event. I naught 0 positive now. And this is very interesting. We know that, as we have discussed multiple times in the past, that the inductor hates the instantaneous change in the current. So this means that at 0 positive, after the switching event will happen, after the switch will be opened, right, you're going to have this portion of the circuit remaining. But right after the switch, there won't be any instantaneous change right away, right? So the inductor is going to behave as a short circuit. So your I1 part of the current is going to remain the same. B part, right? So your I1 0 positive will remain at 0.2 milliamperes. Now let's find I2 0 positive, right? So this is I1 0 positive. Now just imagine that your circuit was literally just this portion of the circuit, right? Two resistors and an inductor. And I am 100% sure that the current through the inductor is not going to change. It is going to remain 0.2 milliamperes. If this current is going to remain 0.2 milliamperes, so just see how the current has to flow. If the current has to flow in this direction, but I2 is originally listed as this direction, so this means that the current in the resistor needs to reverse its course instantaneously, and that can happen in a resistor. So I2 0 positive becomes minus 2 milliamperes. So the same amount of the current is going to flow in the resistor, but in the opposite direction now. So this is I2 at 0 positive. Let's do C part. We have to find the value of I1 of t, right? So C is find the value of I1 of t, right? For t is greater or equal to 0. If you see that I1 of t is essentially the current that is flowing through the inductor. So we know that the direction of the current through an inductor is e raised to power I naught e raised to power minus t over tau. So in order to find this thing, let's find the value of, very quickly, value of tau first. So tau equals L over R, right? For t is greater or equals to 0. We have the portion of the circuit for t is greater or equals to 0 is, this is a resistor, this is a resistor, here's an inductor, right? So we have 15K, 15K, 30 millihenry. So here's an L, two resistors are in series, so I can easily find what was 30 millihenry. Sorry, 30 millihenry divided by 15K plus 15K. So it will come out to be, tau will come out to be 10 to the raised to power minus 6. Okay, so I'm going to replace this value over here. And what is the value of I naught? This, right? So tau is 10 to the 6 minus 6, and I naught is I1. I naught is I1 at 0 positive. So I1 of t becomes 0.2 milliamperes, right? So I1 of t becomes 0.2 milliamperes e raised to power minus 10 e raised to power t over tau, which is 10 to the minus 6 milliamps. And I can rewrite this as 0.2 e raised to power 10 to the 6 times t milliamps. Oh, sorry, minus 10 to the 60. This 10 to the minus 6 becomes 10 to the plus 6 up there. Right, so this is I1 of t, 0.2 e raised to power minus 10 to the 6 milliamps. The other thing that I need to find now is in part D is I2 for 0 positive. So D is, I need to find I2 of t for t is greater or equals to 0 positive. So let's find I2 of t. Again, if I look at this circuit, I know that my I1 is flowing in this direction, right? So I2 is shown over here in the main circuit as flowing downward originally. So if I look at this circuit now, this means that my I2 is just the reverse of I1. So my I2 of t equals to minus I1 of t. So it should come out to be minus 2 e raised to power minus 10 to the 6 times t milliamperes. So this is your D part. The final part of this question is explain why I2 of t is not equal to I2 of, I think I kind of already explained this, right? That in the first part, when we got 0.2 milliamperes, why it was not equal to over here 0.2 milliamperes, why it was a negative of this thing, right? Because there was an instantaneous change in the current in the resistor, as we explained over here. So yeah, maybe I can write it, right? The current in the resistor change instantaneously. right? Okay. So with that, thank you so much. I hope this will clarify some of how to solve these circuits. Literally, all you need to know is the regular equations of the natural responses of the RL and RC circuits and simple Ohm's law and the Kirchhoff's law. All right, thanks, bye.